Chapter 9, Molecular Geometries and Bonding Theories. Please make sure that you have your PowerPoint packet and a pencil available, along with a periodic table, before you continue with this video cast. As we learned in Chapter 8, we can represent various molecular substances, things that are made of non-metals and are covalently bonded, as Lewis electron dot structures. These Lewis electron dot structures have various shapes, and the shape of a molecule plays an important role in its reactivity. The form leads to its function. By noting the number of bonding and non-bonding electron pairs, we can easily predict the shape of the molecule. So what determines the shape of a molecule? Simply put, the electron pairs, whether they be bonded or non-bonded. If we look here, these pair of electrons right here are called a non-bonded pair, and these three are called bonded pairs of electrons. These electrons repel each other, and since they repel each other, they want to spread out around the central atom, in this case nitrogen, as far as possible. By assuming the electron pairs are placed as far as possible from each other, we can predict the shape of the molecule. We refer to the electron pairs as electron domains. In a double or a triple bond, all electrons shared between those two atoms are on the same side of the central atom, and therefore we count them as one electron domain. About this central atom, labeled A, there would be one electron domain right here, one electron domain right here, even though it's a double bond, remember we only count it as one electron domain right here, and then one electron domain right here. Now there would technically be, this one would technically be called a non-bonded electron domain because it's not bonded to something else, and these three would technically be called a bonded electron domains because they are stuck to something else. This one has a total of 4 electron domains. The valence shell electron pair repulsion theory, also known as VSEPR, allows us to predict what the shape of the molecule is, therefore know its form, and then thus say what function the molecule will have. The VSEPR series says the best arrangement of a given number of electron domains is the one that minimizes the repulsions among them. In other words, it spreads them as far apart around the central atom as possible. There are 5 main electron domain geometries, and we will refer to these shapes as geometries occasionally, just like we'll refer to them as specific shapes, but geometry is technically what they are because they have an angle between the bonded or the non-bonded electron domains. We can see here if there are 2 domains, there's a 180 degree bond angle between them to get them as far apart as possible. If there's 3, 120, 4, 109, notice its shape is called a tetrahedral. If there's 5, notice there's actually 3 domains around the center. They call that the equatorial axis, and then you can see that there's an up and down portion right here too. They call that the axial domains. And then you can see right here this is octahedral with all 90 degree bonds. We're going to look at each one of these electron arrangements in detail. So all one must do is count the number of electron domains in the Lewis dot structure, and the geometry will be that which corresponds to the number of electron domains. The electron domain geometry is often not the shape of the molecule, however. molecular geometry is defined by the positions of only the atoms in the molecules, not the non-bonding pairs. So you can see here is a non-bonding pair of electrons. That actually changes the bond angles here between the hydrogen, nitrogen, and hydrogen. We'll talk about that as we go and look at each one of the molecular geometries. Within each electron domain, there might be more than one molecular geometry, depending on how many shared and unshared pairs of electrons we have. Here we have 4 shared pairs. Here we have 3 shared pairs, 1 non. Here we have 2 shared pairs and 2 non-shared pairs of electrons, and that changes the molecular geometry. Now let's take a look at each electron geometry in detail. If there are 2 electron domains, the only shape it can have is something called linear. Linear, you have to memorize the name, linear. 2 bonded domains, 2 non-bonded domains, it would be a 180-degree bond angle between these. An example is carbon dioxide. Note, if there are only 2 atoms in a molecule, the molecule will be linear no matter what the electron domain is, because the 2 bonded domains will want to be as far apart from each other as possible. If there are 3 electron domains, the electron domain geometry is known as trigonal planar or trigonal planar. Trigonal planar. If there are 3 bonded domains and 0 non-bonded domains, the molecular geometry is called trigonal planar or trigonal planar, and an example is BF3. If there are 2 bonded domains and 1 non-bonded domain, then the molecular geometry is called bent. It's because these unshared pair of electrons actually force the BAB angle right here to be a little bit less than the 120 degrees that would normally be experienced in the trigonal planar. You need to memorize these 2 names, trigonal planar and bent. Non-bonding pairs are physically larger than bonding pairs. Therefore, the repulsions are greater, and this tends to decrease the bond angle in a molecule. You can see right here there are 4 electron domains, all shared between the carbon and the hydrogens, which gives you a tetrahedral arrangement and a 109.5 degree bond angle. Here in NH3 you can see there's a non-bonded electron domain right here, and that forces the HNH bond angle to be a little bit less, about 107 degrees. You might not think that's very much, but actually in the physical world it makes a huge difference. Here 2 non-bonded electron domains squishes the bond angle of HOH to be 104.5 degrees, which makes a big difference in how that acts in its solid, liquid, and gaseous phases. Double and triple bonds place greater electron density on one side of the central atom than do single bonds. Therefore, they also can affect bond angles. And you can see here, double bond right here puts a little bit more electron density right here, forcing this chlorine-carbon-chlorine bond angle to be a little bit less than 120 degrees. Going back to the electron domains now, we did 2 electron domains, 3 electron domains, now we're at 4 electron domains. The main electron domain geometry is called tetrahedral. If there are 4 bonded and 0 non-bonded, the molecular geometry is tetrahedral. If there are 3 bonded and 1 non-bonded, it is called trigonal pyramidal or trigonal pyramidal. Notice 1 unshared pair of electrons right here causes this bond angle to decrease to about 107 degrees. If there are 2 bonded and 2 non-bonded, the shape is called bent. And notice this BAB angle right here would be reduced to about 104.5 degrees. Tetrahedral, trigonal pyramidal, and bent. You should memorize those names. If there are 5 electron domains, we then enter what's called the trigonal bipyramidal electron domain geometry. Notice there are 2 distinct positions in this geometry. Axial, that's up and down, and equatorial, which is around the center, like the equator goes around the Earth. This is the axial bond right here, these 2. The equatorial bonds are here, here, and here. And notice the bond angles are different. In the equatorial, there are 120 degrees between. Between the axial and the equatorial is a 90-degree separation. Lower energy conformations result from having non-bonded electron pairs in the equatorial rather than the axial positions of this geometry. And so in the trigonal bipyramidal electron domain geometry, when electrons or bonded domains are lost and there's non-bonded domains, they only happen in the equatorial axis, here, here, and here. There are 4 distinct molecular geometries in this domain. First of all, if there's 5 bonded and 0 non-bonded, it's called trigonal bipyramidal. Trigonal bipyramidal, axial, equatorial, 5 things around, 120-degree bond angle here, 90-degree bond angle here. 4 bonded, 1 non-bonded, it's called seesaw. Notice this one unshared pair of electrons right here squishes these 2 B's together. If you lay it on edge, it would go teeter-totter, and be a seesaw. 3 bonded, 2 non-bonded, this is called T-shaped. Notice 90-degree bond angle here between the BAB. And 2 bonded and 3 non-bonded gives you a linear structure once again with the BAB 180-degree bond angle between the BAB here, with the entire equatorial axis void of any bonded domains of electron. They're all non-bonded. Lastly, the octahedral electron domain. This is when there are six domains of electrons around the central atom. If there are 6 bonded and 0 non-bonded, the shape is called octahedral. You need to memorize that name. If there are 5 bonded and 1 non-bonded, it's called square pyramidal. Notice now in the octahedral domain, the unshared pair of electrons always occurs in what's called the axial domain, the up and down domain right here. Square pyramidal would make a pyramid if the B's would all connect to one another. And lastly, 4 and 2 is called square planar. Notice it's in one plane of existence between the B, A's, and B's right here, and then 2 non-bonded pairs in the top and the bottom. Notice there are always 90-degree bond angles there. There are 3 molecular geometries: octahedral, square pyramidal, and square planar. Larger molecules, it makes more sense to talk about the geometry about a particular atom rather than the geometry of the molecule as a whole. So for example, right here around the carbon atom that I'm circling, it would have 1, 2, 3, 4 bonded domains, 0 non-bonded domains, so it would be called tetrahedral. About this carbon that I'm circling right now, there would be 1, 2, 3 bonded domains, 0 non-bonded domains, and so we'd call it trigonal planar. About this oxygen atom right here, there are 2 bonded domains, here and here, 2 non-bonded domains, one on the top, one on the bottom, and so it would be a bent shape for the actual shape of that portion of the molecule. This approach makes sense, especially because larger molecules tend to react at a particular site in the molecule. In Chapter 8, we discussed bond dipoles, but just because a molecule possesses polar bonds does not necessarily mean the whole molecule will be polar. You can notice here we have a polar bond between carbon and oxygen, or a dipole moment between this carbon and this oxygen, but we have an equal and opposite dipole moment in the other direction. And so now, in terms of polarity, in terms of something having a buildup of positive or negative charge in one area of the molecule, there isn't any. Notice how there's a pull in one direction and equal opposite pull in the other. And so we have to define now a new type of polarity, not just bond polarity, but overall molecule polarity. And it turns out that this overall molecule polarity is the most important or deciding factor. So to be a molecule that is a polar molecule, and therefore has an overall dipole moment throughout the molecule must be asymmetrical. Asymmetrical. In other words, you have to be able to chop it in half. And when you chop it in half, it must be different on both sides, no matter where you chop it in half. By adding the individual bond dipoles, one can determine the overall dipole moment of the molecule. You can notice right here, since it has this bent shape and is asymmetrical, it would have 2 unshared pairs of electrons here on the top. There would be a more negative charge up here at the top of the oxygen, and more positive charge down here on the hydrogens. And it would have an overall dipole moment, therefore water is a polar molecule. Here are some examples. This would be a polar molecule because we have a net overall pull for electrons towards the chlorine. This molecule, called carbon tetrachloride, has a net pull in every equal and opposite direction in its tetrahedral shape. Therefore, even though this possesses 4 polar bonds, the overall polarity of this molecule is 0. This is a nonpolar molecule. This would be a polar molecule simply because it's got an unshared pair of electrons on the top here and it's asymmetrical. this would be polar as well, because there would be an overall pull for electrons towards the chlorine. BF3 would be nonpolar because there's equal opposite pulls in every single direction. Being able to determine whether a molecule is polar or not is critical. Critical information in this chapter. Now let's take a little closer look at the overlap and bonding characteristics between atoms and when and how their electrons are actually shared. We think of covalent bonds forming through the sharing of electrons by adjacent atoms. In such an approach, this can only occur when orbitals in the two atoms overlap. You can see here hydrogen, hydrogen, the s orbitals overlap. Hydrogen and chlorine, the s and the p orbitals overlap. Chlorine and chlorine, you can see the p orbitals overlap. The overlap region is the bonding area. Increase in overlap brings these electron and nuclei closer together while simultaneously decreasing electron-electron repulsion. However, if an atom gets too close, the internuclear repulsion greatly raises the energy. We can see here on this graph, this distance of the nuclei apart gives the least amount of energy and would actually make the perfect overlap. If we get closer and closer still, notice the energy goes up and there will be too much repulsion between the nuclei for it to stick together. If we go out this direction over here, you can see that now there's not enough attraction from one nuclei to the other's electron, and therefore you're not going to have any bond at all. So it's kind of like Goldilocks. It's either too close or too far away, and then there's just right. And this internuclear distance is the important thing for deciding the overlap of the bonding. It's hard to imagine tetrahedral, trigonal, bipyramidal, and other geometries arising from the atomic orbitals that we recognize. Consider beryllium. In its ground state, electronic state, it would not be able to form bonds because it has no single occupied orbitals, and therefore nothing would overlap. But if it absorbs the small amount of energy needed to promote an electron from the 2s to the 2p orbital, it could form two bonds. If it took one electron and popped it up here, now it could form a bond here, and it could form a bond here because it'd have an open orbital to share an electron with something else. Mixing the s and the p orbitals yields two orbitals of the same energy that are hybrids of the two orbitals. The word degenerate means of the same energy. That's how I read it. Yields two of the same energy orbitals that are hybrids of the two orbitals. These s and p hybrid orbitals have two lobes like a p orbital. One of the lobes is larger and more rounded, as is the s orbital. These two orbitals of the same energy would align themselves 180 degrees from each other, and we can see here these purple orbitals right here would align themselves on opposite sides of the beryllium and therefore be able to bond with some 2p orbitals from fluorine. These hybridized orbitals right here are called an sp hybrid orbital because it took the s's and the p's and stuck them together. Look back here on this last slide. An s orbital and a p orbital combined to form this hybrid orbital called an sp hybridized orbital. So when something forms two bonds, they have sp hybridized orbitals. This is consistent with the observed geometry of beryllium compounds. They're linear, and so that's why we think this happens. With hybrid orbitals, the orbital diagram for the beryllium would look like this. Notice how there is an s, a 1s orbital, then there would be the sp hybridized orbital, and then there would be the empty 2p orbital, because one of the 2p orbitals went and joined together with the 2s orbital to form this sp hybridized orbital. Now each one of these unshared pairs of electrons or unshared electrons could go and form a bond. The sp orbitals are higher in energy. The sp orbitals are higher in energy than the 1s orbital but lower than the 2p. Energy-wise, they fit in the middle. Using a similar model for boron would lead to three degenerate sp2 orbitals. We can see that in boron, let's back up just a second right here, boron has an electron configuration at 2s2, 2p1. So you'd think that it only formed one bond because it's got one unpaired electron. But if you just absorbed a small amount of energy to promote this electron over here, now you'd have 1, 2, 3 unpaired electrons, and this could form new orbitals called sp2 hybridized orbitals. And as a matter of fact, that's what it does. These three hybrid orbitals, 1, 2, 3, comboed to form 1, 2, 3 hybrid orbitals, are called sp2 hybrid orbitals, not sp squared, sp2 hybrid orbitals. And this is consistent with what boron usually forms. 3 bonds and a trigonal planar geometry. Moving forward, let's take a look at carbon. If you look at carbon, here's a pair of two S's and 1, 2 unpaired. How about if we put a little bit of energy into it, promote this electron over to here. If we do, we now have 1, 2, 3, 4 electrons. Hybridize them so they're all the same energy, and now we have sp3 hybridized orbitals, and now carbon can go very happily form 4 bonds, which is exactly what it does. You can see right here, here's the s, p, p, and p orbitals hybridize all together to form 1, 2, 3, 4 orbitals, and we say that this is sp3 hybridized. And notice it makes that classic 109.5 degree bond angle tetrahedral arrangement that carbon usually forms, and it will form 4 bonds with something which carbon always absolutely loves to form. For geometries involving expanded octets in the central atom, we must use d orbitals in our hybrids. So you can see here s, p, and 1d from these guys right here. So these would be elements that are in the 3rd period or below, and now we would say that this is sp3d hybridized. Notice it can form 1, 2, 3, 4, 5 bonds, and that's exactly what it does. And it leads to the 5 same energy, remember that's what the word degenerate means, same energy sp3d orbitals, and of course the same thing then would happen with an octahedral arrangement where we would have 6 degenerate orbitals that are called sp3d2. Remember the word degenerate means same energy. 6 of the same energy orbitals. 1, 2, 3, 4, 5, 6, and it forms that great octahedral arrangement once again. So once you know the electron domain geometry, you also know the hybridization state of the atom. In this case, linear, hybridized sp. 1, 2, 3, you now know it's sp2. 1, 2, 3, 4 domains, now it'd be sp3 hybridized. If there's 5 domains, it's sp3d. If there's 6, it's sp3d2 hybridized. So hybridization is a major player in what's called the valence bond theory of approach to bonding. There are 2 ways orbitals can overlap to form bonds between atoms. First one is called a sigma type bond. This is where there's a head-to-head overlap between 2 orbitals. It's a cylindrical symmetry of electron density about the internuclear axis. Internuclear would mean between this nuclei and this nuclei. It would form this head-to-head overlap right here that would actually, if we looked at it from the side, be in the shape of a cylinder. Pi bonds, or second bonds or third bonds that occur between 2 atoms are characterized by side-to-side overlap. The electron density is above and below the internuclear axis. Single bonds are always pi bonds because sigma overlap is greater, resulting in a stronger bond and more energy lowering. Multiple bonds, one of the bonds is a sigma bond and the rest are pi bonds. You can see here we have a double bond, one of them is a sigma, the other one's a pi. Here we have triple bond, one of them is a sigma and 2 of them are pi bonds. In a molecule like formaldehyde, shown on the left, an sp2 orbital on the carbon overlaps in a sigma fashion with the corresponding orbital on the oxygen. The unhybridized p orbitals overlap in a pi bond fashion. You can see right here this carbon does a head-to-head overlap with the oxygen, forming a single bond, which is much stronger than the second part of the bond, which has a overlap above and below, where the p orbitals actually lean over and kind of overlap with each other, and these are called a pi bond. In triple bonds, as in acetylene, 2 sp orbitals form a sigma bond between the carbons, and 2 pairs of p orbitals overlap in pi fashion to form 2 pi bonds. You can see here's the head-to-head overlap right here, sigma bond, strongest of them, and then the top and the bottom make one of the pi bonds, and the side and the side over here make the second pi bond. So there's 1 sigma and 2 pi's inside of a triple bond. When writing Lewis electron structures for species like the nitrate ion, we draw resonance structures to more accurately reflect the structure of the molecule or the ion, because the double bond can be here, here, or here. In reality, each of the 4 atoms in the nitrate ion has a p orbital. The p orbitals in all three oxygens overlap with the p orbital of the central nitrogen. So you can see here the p orbitals are overlapping, and they give like a third of a bond or so. This means that the pi electrons are not localized between the nitrogen and one of the oxygens, but rather they are delocalized throughout the ion, and that's why we say it's like a third of a bond, a third of a bond, a third of a bond, because the electrons are zooming between all of those different places. The organic molecule benzene has 6 pi bonds and a p orbital on each carbon atom. In reality, the pi electrons in benzene are not localized but delocalized, and that's why they have this picture right here. Just remember, a benzene ring, if you look back at the slide before, actually has this circle right here to indicate that resonance occurs between these. The resonance that occurs is the sharing of these p orbital electrons. The even distribution of the pi electrons in a benzene makes this molecule unusually stable. This idea of resonance and also this idea of pi bonds, I'm just going to back up a couple of slides here, also explains an interesting trend that we saw in Chapter 8. Remember how sigma bonds, we said, are the strongest bonds because they have this head-to-head orbital overlap right here. In a double bond, though, we have a sigma bond, which is strong, and then we have a pi bond, which is represented by the above and below right here, which is a little bit weaker. And if you remember when we talked about bond energies in Chapter 8, we said that a single bond, for example a carbon-carbon single bond, had a bond enthalpy of about maybe 350 kilojoules per mole or so. And then we said a double bond, though, is not double the strength. So if we say, for example, the carbon-carbon single bond is 350 kilojoules per mole, the carbon-carbon double bond is not 700. It's actually only on the order of about 600. And this is the reason why. It's because the sigma bond is so much stronger, giving 350 kilojoules per mole, for example. And then the second bond, being a pi bond, is actually maybe only 200 kilojoules per mole strong or something like that, and gets us only to 550 or 600 kilojoules rather than the 700 that we'd expect. Same thing happens with the triple part of the bond. If we look at the third bond, it's actually another pi bond, which is weak just like before. And that's why the triple bond is not 3 times as strong as a single bond, because there's different types of bonding that are going on. This wraps up the shapes, polarity, and molecular geometry theories for Chapter 9. Good luck with your bonding and structure homework.